Okay, so in the last video we introduced the idea of generalized momenta and ignorable coordinates. Now we're going to go and take a look at how to handle constraint forces in the Lagrangian formalism. So the in Newtonian formulation, we would have to construct some constraint force, be it friction or whatever, normal force, to describe the motion and factor in the constraint. Sort of the genius of Lagrangian mechanics is that we don't need to worry about the constraint forces. The generalized coordinates make it all go away. But there is a way out. If for some reason it makes sense to analyze the problem with Lagrangian mechanics, but you still need to know the forces, there is a technique called Lagrange Multipliers. So to do this, to get a handle on how this goes, we're going to have to go all the way back to the least action principle. So just for the moment, let's look at a two-coordinate system connected by one constraint. And remember, in general, we can write our constraint as f of q1, q2, and the time equals 0. All right, so now let's go ahead and calculate the variation on the action for this system. So the variation on the action will be the variation in the integral t1 to t2 of the Lagrangian dt. So that'll be integral 1 to t1, t1 to t2, sum over our coordinates, partial L partial Qi minus d dt, partial L partial Qi dot, variation in the Qi dt equals 0. Okay, we saw that before. So now let's go ahead and explicitly break out the sum. So this will be equal to the integral t1 to t2 of, I guess I'll want some curly brackets for once, and then I want some square brackets, partial L partial q1 minus d dt of partial L partial q1 dot times the variation in q1 plus partial L partial q2 minus d dt partial L partial q2 dot times the variation in q2 dt, and by the least action principle we have to demand that equal 0. Alright, that's all well and good. Now, before, what we were able to do was, when the variables were all independent of each other, because we had already chosen generalized coordinates that took the constraints into account, we could just say, well, each term in brackets has to independently vanish, but here we can't say that, because the problem is these two terms now are not independent. Our variation in Q1 depends on our variation in Q2. Now, the way way we get to dodge those, we go back and look at our constraint function right here. So at any given time t, whatever time we pick, our function f is fixed. So that means we can demand that the variation in f be 0. So that would mean that partial f partial q1 times the variation in q1 plus partial f partial q2 times the variation q2, that's got to be 0. All right. So we can figure out how the variation q2 depends on q1. We can solve this for the variation q2. So variation q2 will equal minus partial f partial q1 over partial f partial q2 times the variation q1. So now the game here is we're going to take that and we are going to stick it right in there. All right. So we'll do that. So now my variation in the action, which I demand is 0, be equal to integral t1 to t2. So we'll have partial L partial q1 minus d dt, partial L partial q1 dot. That's the first term. Then the second term, partial L partial q2 minus d dt of partial L partial q2 dot. And then we have to multiply that, because the idea is I want this all being multiplied by variation q1, so I need this fudge factor here. So the plus has already become a minus sign from that fudge factor. And then I need to times it by partial f partial q1 over partial f partial q2. All right. Times variation q1 dt. Yeah. Excellent. So now we still have to demand that the integrand here, or the thing in the curly brackets, vanishes for all time. So that tells me partial L partial q1 minus d dt of partial L partial q1 dot has to equal, leave the square brackets in, partial L partial q2 minus d dt of partial L partial q2 q2 dot times the thing in parentheses, partial f partial q1 partial f partial q2. All right. So we can rearrange this a bit. We can at least get, the nice thing here is this is actually separable. So we're going to separate it. So I'm going to use my copy and paste math here. Oops, didn't mean to do that. Copy, paste. Copy, paste. All right. This have to be equal. Get rid of those brackets there, bracket there. And then we will divide this by both sides by partial f partial q1. And we are left with being divided by partial f partial q2. So yay, it is separated. So we've got the q's separated, but there's still an implicit and possibly an explicit dependence on the time. So what we do is we demand that both these terms be equal to the same function. So this is like when you've separated things before in differential equations. You would go and find a separation constant. Here it is a separation function, and for convenience we'll call it minus lambda of t. And this function lambda gets called the Lagrange multiplier. P-L-I-E-R. There we go. All right. So the reason why we do it that way is that then I can rewrite my Lagrange equations. For instance, I can rewrite this one here as partial L partial Q1 minus d dt of partial L partial Q1 dot plus, that's why I did it that way, lambda of t partial F partial Q1 equals 0, and similar for Q2. All right. So that's how you would do it if you had two coordinates connected by one equation of constraint. Let's say it's more general than that. I will hope that you can believe me that the general case where we have n coordinates and m equations of constraint becomes partial L partial Qi minus d dt of partial L partial Qi dot plus, and here it comes, sum over j lambda j of t partial fj partial qi equals 0. We let I run from 1 to n and j run from 1 to m. All right. So let's inspect these terms a bit, shall we? If I add the ddt term here to both sides, so let's do a little more copy-paste math here. So we'll copy that, paste there. We'll keep with this, copy that, paste it there. We're going to get rid of it being equal to 0, because instead we're going to move this bit to the other side. There we go. So now let's see how we can interpret this. If we look here, we've already worked out that this is going to be here, the time derivative of the generalized momentum. And we've already worked out that this just gave me a force. So this would be my conservative forces all here. And so then I interpret this term as being my constraint forces. So that this whole thing can be seen as a sum of forces. Now we kind of got to put that in quotes because it could be torques, right? So in fact, because it could be torques, we call the generalized force, or generalized force of constraint. We call it capital Q. Every book seems to do that. Well, if we just define that to be sum over J of all of my Lagrange multipliers times partial Fj partial Qi. All right, so like I said before, these constraint forces could either be forces or torques. So let's go do an example, shall we? Let's have a disk rolling down an inclined plane without slipping. I know you've done this in lower division mechanics before. That's why we're revisiting it here. You already know the answer. So let's say that the length of the incline here is L. A good choice of generalized coordinate would be to locate the center of mass here. We'll call that distance y. And then, because this is rolling, we can imagine putting some mark on here and seeing the angle through which we've rolled here is theta. Just for completeness sake, we'll say that the radius of the cylinder is r. And we will say that we are inclined at angle alpha. All right. So we know from the rolling without slipping condition that y has to equal r theta. Now we've got to write this as a proper equation of constraint. So in other words, you got to make it equal to 0. So my f of y and theta will be equal to y minus r theta, and we demand that equals 0. Okay, super. So that's my constraint equation. All right, and I can go ahead and write my kinetic energy. That'll be 1/2 my dot squared. Then we'll have the rotational part, which will be 1/2 I theta dot squared. And we'll put in what our I is, so 1/2 my dot squared plus 1/2. It's a disk, so 1/2 mr squared theta dot squared. And I guess we can clean that up just a little bit more. 1/2 my dot squared plus 1/4 mr squared theta dot squared. Super. And then for the potential energy, we can just go with, if this is 0 down here, my height will be equal to okay, so mg, my height will be L minus y sine alpha. Awesome. So my Lagrangian is T minus V. So it'll be 1/2 my dot squared plus 1/4 mr squared theta dot squared minus mg. Actually, let's make it plus. We can be cute. Y minus L sine alpha. Super. Now, normally, if you didn't care about the constraint, forces, at this point we would pick either theta or y, probably y to be my go-to one here. And I'd be looking at this and going, my God, that's y dot squared, and I would insert that and turn the crank. In fact, at the end of this, I will do just that, just to show that if you don't need the constraint forces, you should try to avoid, you should exploit all of your constraint equations and get your Lagrangian cleaner. So anyway, though, my Lagrangian equations of motion with the Lagrange multipliers become partial L partial y minus d dt of partial L partial y dot plus lambda. It's not going to depend on t here. Partial f partial y equals 0. That's one of them. And the other one here will be partial L partial theta minus d dt of partial L partial theta dot plus lambda partial f partial theta equals 0. So that's my system. All right, well, let's go ahead and plug in. So this first one, partial L partial y. Okay, so I pick up an mg sine alpha from that. All right, partial L partial y dot. Okay, I just got this guy, so I get my dot. Differentiate that, that becomes y double dot, so minus my double dot. And here, if I go back and look at my equation of constraint, that's y minus r theta, so partial f partial y is just 1. So we'll just have plus lambda equals 0. All right. And then for the second one here, partial L partial theta, nothing. All right. Now don't make the mistake of saying, ooh, theta's ignorable. Okay. Because we're connected by the constraint between theta and y. So then we'll say minus, okay, so my theta dot stuff, okay, yeah, here it is. So I bring down 2, that'll give me a half mr squared theta double dot minus lambda, and then my partial f partial theta is going to give me a minus r. So I already factored in the minus sign there, but there's the r. That equals 0. All right. So for what's worth, we can divide both sides through by an r to kind of make it go away a bit. And so I do get my let's see, yeah, we can rewrite this just a little bit as 1/2 mr theta double dot plus lambda equals 0. So that's that. And then from here, I'm just trying to eliminate the Lagrange multiplier. So if I subtract these guys here, I'll get mg sine alpha minus, okay, I'll have my double dot minus 1/2 mr theta double dot equals 0. Now here I'm going to have to use my equation of constraint again. Remember we said that f was equal to y minus r theta equals 0. So that means that r theta equals y, so r theta double dot is y double dot. So we still have to do that, okay? So then this turns into, oh, let's divide everything through by m while we're at it. Super. So this turns into g sine alpha minus 3/2 y double dot equals 0. So we get y double dot equals 2g sine alpha over 3. All right, now if we take that, so let's go and take this guy again. Recognize that this guy here is y double dot. If we go ahead and take that and substitute that in for the y double dot, we can solve for lambda. So let's do that. So I have 1/2 m, then my y double dot is 2g sine, whoops, sine alpha over 3 plus my lambda equals 0. So my Lagrange multiplier, which turns out not to depend on the time, so that's why I never bothered writing of t, will be, cancel, cancel, minus 1/3 mg sine alpha. Yeah. All right, so now that I got my Lagrange multiplier, I can go ahead and put back in to here to get, let's see, we already canceled the m's, right? So 1/2 r squared theta double dot will be equal to minus 1/3 g, oh yeah, m r squared theta double dot minus 1/3 mg sine alpha. Cancel the m's. And so we are left with, oops, I'm sorry, this is 1/3. There we go. Oops, and that's plus because we brought over to the other side. Yeah. So then we get that theta double dot equals 2g sine alpha over 3r. Super. And we can integrate it twice. So we can integrate my y double dot twice to get the position, and my theta double dot to get the angle through which I've rolled. Or I can just solve for one or the other and use the equation constraint to connect them. All right, the real payoff here is getting to our generalized forces. So let's take a look at the QY generalized force. So they'll be equal to lambda times partial f partial y. Well, that's just lambda, because remember partial f partial y was just plain 1. So it'll be minus 1/3 mg sine alpha. Okay, minus sign means we're pointing in the opposite direction of increasing y, which is down the ramp. So that means this generalized force points up the ramp. Can you think what force that might be? Yeah, it's friction, static friction. And then let's go take a look at our Q theta generalized force. It's not really going to give us anything new, but it's worth looking at. So that will be equal to, remember the partial f partial theta is equal to minus r, so this will be minus lambda r. So this will be equal to plus mg r sine alpha over 3. And that will be the torque due to the friction. There we go. So that's how you go about getting your generalized forces there. Now, let's say we didn't want the Q's. Let's go and show how we could get the equations of motion a lot quicker. So we'll go back to what we had before, and I will just copy and paste it over. Copy, paste, put that there. Now, if we use our equation of constraint, we would have looked at this and said, this is y dot squared, okay? So then we would rewrite our Lagrangian as 3/4 my dot squared plus mg y minus L sine alpha. So now we've only got, our Lagrangian only depends on one variable, so let's do Lagrange's equations of motion on it. Partial L partial y minus d dt of partial L partial y dot equals 0. So partial L partial y, that's just going to be mg sine alpha. Partial L partial y dot, this will be 3/2 my dot. Then differentiate that with respect to time, becomes 3/2 my double dot equals 0. And once again, we can cancel the zeros and the m's into the void of 0. And we are left with y double dot equals 2/3 g sine alpha. And we just go ahead and integrate twice, just like we did before. So that's a heck of a lot faster. So if you don't need the generalized forces, then by all means use your constraints. Even if it takes a little bit of extra work to set up the Lagrangian, it will make the analysis of the Lagrangian equations of motion go a whole lot smoother. All right, so in the next video segment here, we're going to go ahead and take a brief look at extending our idea of generalized forces, and we're going to explore D'Alembert's principle. Okay.